So we have defined homotopy groups, and we have a way in some sense of computing them, which is that you can pass to the universal cover. But let's see how we can use them. So there is an obvious way, similar given what we've done with pi1, okay, which is that we will look at the following extension problem. We have f from Sn minus 1 to x. Okay, so does this extend to a map, capital F mapping, say dn to x. Okay, but maybe for the convenience of the statement, let me make this Sn. So for example, n is 1, and you want to extend it to dn plus 1 x. So the following theorem. Okay, so recall that this is useful not just for doing it for Sn specifically, but inductively, step by step. We have been doing this when we were talking about disks. So here is the theorem. Every f from Sn with some base point. I ignore base points for now. To x extends to capital F from dn to x if and only if pi n of x with base point x0 is equal to is trivial. Okay, so let me just say n is greater than or equal to 2x path connected, and so x0 is a point in x. Okay, so first let's take care of base points. So first a statement which is the following proposition: if x is path connected and x1, x0 are in x, then pi n of xx0 is isomorphic to pi n of xx1. So a fundamental group doesn't depend on the base point that we are taking. So this is a proposition in itself, which I didn't prove earlier. So let's prove this. Proof is the idea is that we have to take a map which is an isomorphism between these two. So given a path alpha from x1 to x2, x0 to x1. Okay, we define a map, well, whichever way you want, pi n of, let's say, xx0 to pi n of xx1. Maybe we'll reverse it. We'll have it from x1 here to x0, and this is the map which we had previously, which is given f. This goes to, so f ends with x, so we'll take alpha inwards here. So alpha begins at x0 and ends at x1. If you wanted the map the other way, you would get it by this. Okay, so this is what we defined as the operation of alpha on the space. So this is if you f mapping to alpha star f as previously, and then we can observe this is a group action, and in particular alpha bar star alpha star f is E star f, which is the f itself. These are homotopic to f. Okay, so this is invertible, an isomorphism. So we have seen another useful fact, base point independence of fundamental groups, and this was because of this external product, pi1 acting on the given homotopy group rather than in the pi1's case where it acted on itself. So that was the first step to these. Now given this, we can take a favorite base point and assume that the fundamental homotopy group with that base point vanishes. And now we can prove the two sides of our result. Okay, so suppose firstly, one is suppose we know every map extends. That is every f from Sn to x extends. And we have a map theta, which represents our element 0, 1 to the n and boundary of 0, 1 to the n. By the way, I should emphasize every time I'm talking about boundary of the cube, not the nth power of the boundary. So this is the entire boundary. We have map, so let theta be this thing to x, x0. Our map, and this is going to be a cube. So we get theta bar mapping Sn to x. Well, and in fact I can take a favorite point here. Let's go to some star to x, x0, where we take a quotient by quotient of Sn is going to be the 0, 1 to the n quotiented out by boundary of 0, 1 to the n. Okay, so far so good. Well, so now we have a map. Do we extend this? To whatever we want to call it. Let's call it some capital theta mapping dn plus 1 to x. Okay, now that we have it, we can define a homotopy. Yeah, so we define a homotopy from theta to E, the constant map in the group. Okay, and that we use the same picture as we used before. That is, we have the sphere, and we can take a whole family of spheres inside it. Okay, so this is the base point star. This point is the base point star. So this goes at all times to. Okay, so first we have a family of maps. From Sn to x, and they're all going to send a base point. Okay, and in fact, Sn comma star to x, x0. Okay, now this is the same trick that we did in S1. So these are just a family of spheres. We can't make them smaller and smaller, otherwise the base point wanders. Now we compose with quotient map. In by boundary in to Sn my Sn. So the disk quotiented with its boundary as a point is a sphere. So you compose with a quotient map, we have a family of maps on this, which is going to be the required homotopy. Now let's look at things the other way, which is very similar again, where we are now, so suppose this time we have the homotopy group vanishing, pi n of x, x0 is trivial, and this time we note that it's true for all x1. In x, we also have pi n of x, x0. It's trivial. Okay, so I've assumed that space is path connected. By the way, because this is an abelian group for n greater than or equal to 2, I'm writing it as 0 rather than the identity group. The same proof works for n equals 1, which we did earlier. Okay, and now what we have to say is that we are given f from Sn to the space x. Okay, and let's say, because the base point doesn't matter, Sn and its sort of favorite base point star maps to x and x0, because otherwise we'll just rename something else as x0 since everything is base point independent. Remember, this is the quotient 0, 1 to the n. So what I've done is, if I take a square or a cube and quotient the boundary to a point, I'll get a sphere. Okay, so a square and the boundary to the point, I'll get a sphere. So I've got 0, 1 to the n, and quotiented out by boundary of 0, 1 to the n. This is f. Given f such that this happens, you define theta using this quotient map. So we have a quotient map here. So this is a theta from 0, 1 to the n, and the pair which will send boundary of 0, 1 to the n to the pair x, x, 0. So by hypothesis, we have H. We have a homotopy. We have H mapping 0, 1 to the n plus 1. And I should say the entire boundary of 0, 1 to the n plus 1 goes to x, x, 0. Okay. So now extend Sn is so. So now in the case of a square, it's easier to see. In the case of cube, you'll need a bigger picture. If I quotient these entire three sides to a point in the square, what you get is still a disk. Okay. So if I draw a cube, well, you would see this in the case of a cube as well. So if I take a cube like this, on the base we have the map defined here. This is what we call theta, and we have a map from the sphere that corresponds to this. So now suppose we quotient by the entire front face, back face. Okay, so we quotient so this picture, it will become utterly unclear. So you take all faces except the base, quotient by all faces except the base. Sorry, this is not quite accurate. Let me strike this out. It's not quite an entire boundary. The base, only the boundary of the base goes to the identity, but all the sides go to the identity, and the top goes to the identity because we have a homotopy to the identity map. So you quotient by all faces except the base, and you will get f mapping the d n plus 1 to x. Okay, this is well defined because the top is the identity, and hence it maps to the identity, and the sides all map to the identity by condition of the homotopy, and the base itself has identification. This boundary gets pinched to a point, and that is exactly the original map, extending f mapping Sn to x. Okay, so we see homotopy groups determine extension problems, and now we'll see a nice interplay between what we have seen, CW complexes, passing to universal covers, and extension of maps to be able to say useful things using higher homotopy groups, to the extent that we can describe them. As I said, the big barrier is that we are not doing homotopy theory to the extent we can study the higher homotopy groups, except showing they vanish in some cases.